Now let's jump back to the search problem. At this point, you should be thinking, there may be a way to find the item in log of n operations. And we need to somehow eliminate half of the items on each operation. In the number guessing game, our guess was always the halfway point of the possible numbers. One way to emulate this strategy is to visit the halfway point of the collection. For example, if we have a stack of 16 items, then we can visit the 8th item. If the 8th item's name is alphabetically greater than the item we're searching for, then we can eliminate items 9 through 16. We would next visit the 4th item, and so on. Notice that this strategy requires the items in the stack to be alphabetically sorted. We didn't have to sort in the guessing game, because numbers are naturally sorted. If the items are not sorted, we can sort them in O of n times log n operations using merge sort. Since the cost is greater than O of log n, or even O of n, is this strategy actually worse than cycling through all the elements? Not quite, because we don't have to sort every time we search the collection. In fact, we only have to sort once. After that, we just need to make sure that the collection remains sorted as items are added, updated, or removed. Inserting or deleting items in an ordered stack requires O of n time. This is significantly shorter than merge sort, but it is still a concern if we frequently update the collection. Now then, can we search a sorted stack in O of log of n time? Unfortunately, no, because we cannot jump to the middle of a stack in a single operation. For example, to inspect the 8th element, we must first pop the elements 1 through 7 from the stack. This is already n divided by 2 operations, or O of n. We are limited by the stack interface, which only allows us to operate at the top of the stack. Thus, it is time to explore other types of collections. Real computers have arrays, which allows us to access any element in one operation. Thus, we could search an ordered array in O of log n time. Insertions and deletions still take O of n time with arrays. Is this good enough? It seems unlikely that we can do better than O of log n for search, but maybe we can do better than O of n for insertions. People soon realized that if we change the structure of the collection to a tree, then we can insert faster while maintaining the fast search time. Take a look at the following tree. This is a binary search tree, or BST. BSTs are trees that have a few additional rules. 1. Each node has 0, 1, or 2 children. All descendants to the left of a node are less than the node. All descendants to the right of the node are greater than the node. For example, all descendants to the left of 5, which are 1, 3, and 4, are less than 5. And the node to the right of 8, which is 9, is greater than 8. Here is the text representation of a BST node. Value is the node value, left is the left child node, and right is the right child node. Using nodes, we can represent the BST as follows. This tree has 7 elements. The height of the tree is the count of the nodes between the root and the leaf that is furthest from the root. In the tree above, there are 4 leaves which are equidistant from root 5. 1, 4, 6, and 9. So let's just pick the node 9. The nodes between 5 and 9 are 5, 8, and 9. So the height of this tree is 3. Let's try searching this tree for some value. As with stacks, our assumption is that we can only see the value of one node at a time. Our example tree is small, so we can actually see the whole tree. But in popular applications, trees can contain millions or billions of nodes. Every tree operation starts at the root node. The search procedure is as follows. If the node value is greater than the value we're looking for, then move to the right child. If the node value is less than the value we're looking for, then move to the left child. If the node is a leaf and the node value is not equal to the value we are looking for, then the tree does not contain the value. For example, suppose that we're looking for 6. We begin at node 5. 6 is greater than 5, so we move to the right child. We're now in node 8. 6 is less than 8, so we move to the left child. And we're now in node 6. 6 is the value we're looking for, so we confirm that the tree contains 6. As another example, let's look for 2. We begin at node 5. 2 is less than 5, so we move to the left child. We're now in node 3. 2 is less than 3, so we move to the left child. We're now in node 1. Node 1 is a leaf, but it is not the value we're looking for. Thus we conclude that the tree does not contain 2. In both cases, we inspected 3 nodes. Notice that every time we moved left or right, we eliminated around half of the possible nodes, just as we did in the number guessing game. Does this mean that the search performance of BSTs is O of log n? Yes, but only if the tree is balanced. Unfortunately, not all BSTs are perfectly balanced like our example above. For example, consider the following tree. This is still a BST because it meets the following criteria. Every node has 0 or 1 child, and all descendants to the left of the node are less than the node. Here's the text representation. The search process for this tree is same as a stack. We are visiting nodes one by one until a node is found. In the worst case, we have to visit every node. As we just saw, we may need to visit many more nodes to search an unbalanced tree compared to a balanced tree. A BST is balanced when, for all nodes, the height of the left and right subtrees differ by at most 1. For example, consider this tree again. Is this tree balanced? At the root node, the height of the left subtree is 2, and the height of the right subtree is also 2. At nodes 3 and 8, the height of the subtrees are all 1. So the difference in heights of the left and right subtrees are all 0. Thus, this tree is balanced. Here is the other example. The root node does not have a right child, so the height of the right subtree is 0. The height of the left subtree is 4. 4 minus 0 is 4, which is greater than 1. So this tree is not balanced. Here is the final example. The height of the left subtree of the root is 3. The height of the right subtree of the root is also 3. The difference between heights is 0. But we also need to check the other nodes. The height of the left subtree of node 8 is 2, but the height of the right subtree of 8 is 0, since node 8 does not have a right child. The difference in heights is 2, so the tree is unbalanced. In the next few lessons, let's study how a BST becomes unbalanced and how we can restore the balance.